Hello everyone, and welcome back to another Eng 130 video tutorial. In this tutorial we'll continue our theme of vector addition, but this time instead of using the parallelogram method, we're going to use Cartesian vector notation. And personally this is my favorite because I find it much simpler than the parallelogram method. And although this concept today will seem really simple, I really strongly suggest you guys study it well because it will help you for the rest of the course. Alright, so looking at the example, you guys may notice that this is the exact same example as example 1.1, where we found the resultant force and its direction measured counterclockwise from the positive x-axis of these two vectors, except this time instead of the parallelogram method, we're going to use Cartesian vector notation. So, what is Cartesian vector notation? Well, it's the idea of any diagonal vector. Let's say you have a vector like this, that this vector right here can be split up into two parts, in 2D of course. In 3D it's a little bit different, but we'll talk about that later. Let's go green because I'm just showing you. So this vector is actually composed of two smaller vectors, a horizontal vector as well as a vertical vector, which I'll make another color just to really show you guys what I'm talking about. So from these two smaller vectors, if we combine them together, we'll actually get that diagonal vector. And that's the whole concept of Cartesian vector notation, is that a vector can be split into what we say its components. So in 2D, there's two components. There's an x component and a y component. And of course, in 3D, there's that third component, which we call the z component, which for this case would be in and out of the page. Now, we'll always give you guys an axis to reference. If not, then you can assume it's the standard axis, which we see here. So for here, our x component is going to be horizontal, and we got a vertical component here, which is what I call the y component, the vertical component. So if I have a vector, and this is kind of how I label these. So let's say that this is vector f. What I like to label the smaller ones is this is f sub v, so the vertical one. Actually, it's probably better to do it like this because in 3D it'll get a little bit more complex. So we'll call this one f sub y, and then we'll call the horizontal one f sub x. So this is really nice. We can split this vector up into two smaller vectors, which is what we're going to do to start with this example for our two vectors here. And then what's really nice is once we have these components, the fx and fy, we can actually start combining them with other vectors to give us the magnitude. And it's actually really, really simple. But let's not get too far ahead of ourselves. Let's just start with the example and start finding us our components of each vector. Alright, so those colors look a little too much like Christmas for me, so let's pick a different color to start. So let's start with the first vector, which will now be the blue vector, not Christmas colored vector. So this will be the blue vector. So right off the bat here, we see it's a diagonal vector, and what we can do is we can split this into two components. Now, if I'm drawing it on the sheet here, what I like to do, instead of using a bunch of colors, it'll look like a Skittles pack by the end of it. What I'm going to do to show its components is use the same color, but a dashed line. So this vector here, the 800-pound vector, is composed of two components. We got the horizontal component, which will go something like this. And then we got a vertical component, which goes straight up like this. So I always put little arrowheads on these components too, just to show that they kind of what they are. So this is the 800-pound vector, but it's kind of hard to go 800 with the little x at the bottom and 800 with the lot. So I'm just going to call this vector right here f1 to make it real simple. So this vertical one is going to be f1, and we know it's the y component, and the horizontal vector is going to be f1 with the x components. So we already split it into two vectors. So now what we need to do is we need to find those components, the f1y, f1x. And what's nice is it follows the geometry. So if we know, let's say, one of the angles of this triangle, say this angle right here, then we can just use simple trig to solve for the magnitude of these components, because this triangle right here has a hypotenuse length. So this length right here is 800. Oh, sorry. So this length is 800, which we know is just the magnitude of the vector. So knowing this angle, which down here we'll call theta, as well as the 800, we can solve for the lengths of those components, which is their magnitudes. All right, so let's just start with the theta real quick. Since this is 40 degrees, we know that the angle here is going to be 50 degrees. And I know you guys all know that, 90 minus 40. However, if you guys wanted, and now this doesn't matter, it's completely up to you. I always like to have the angle with the horizontal axis. To me, it just, I don't know, it's always been standard for me, but you guys don't have to go that way. Keep in mind that the magnitude of F1y over on this side is going to be the exact same as if I went like this and had F1y coming up like this, and then F1x coming across like this. That those F1y and F1x, those are going to be the exact same. And in this case, you don't even have to try and find the angle. You already know that it's 40 degrees. So it's completely up to you, whatever you guys are comfortable with. Either way, you'll get the same answer because the magnitudes of those components will be the same. However, like I said, I don't know why, but I just prefer having the angle with the x-axis. It's just kind of always what I've done. So I will stick in blue so we can go through. So if we know that the hypotenuse length is 800 pounds and our angle is 50 degrees, then we can go down here and say that F1, and I'll start with x because why not? It's going to be the hypotenuse. So right here we got 800, and then we're going to have to multiply it using trig by sine, oh sorry, that's if we did it the other way. This is why I prefer having with the x-axis, because F1x will always be the cosine of the angle. So 800 times the cosine of 50 degrees. And if we type that into our calculator, we'll get 514.2, oh, I always click the button, 0.2 pounds. All right, so that was really, really simple. So we can do the same thing for the vertical component. So F1y is going to be equal to, again, 800. This time it's going to be sine of 50 degrees. And if we type that into our calculator, we're going to get 612.8 pounds. Alrighty, so that's basically the hardest part of these examples, because after this it's just some simple addition. So knowing this trig is the hardest part. Alright, so now with these components we can actually denote our vector using a very specific format. And you guys are going to want to remember this format because for the first part of the course, this format is kind of how you'll describe all vectors. And when we get to 3D vectors, you'll do the same. So what we do is we say that F1, and since it's a vector, we should put the arrowhead on top because we're talking about the whole vector right here. It's going to be equal to, and then this is where the format starts. So what we want is, since it's a vector, we want squiggly brackets. And then from the squiggly brackets, we can begin putting in our components. So the first component is going to be an x component. So it's going to be the 514.2, and since this is the x component, and this is where you guys will want to pay attention, I'm going to highlight this in red, is x components, when we label our vectors, are denoted with a kind of a fancy I. So we say 514.2 and we go I. And usually, and this is what I've seen, profs do it differently, so don't take just what I do. Keep in mind it could be a little different depending on the prof. Is I put a little squiggle at the bottom of the I, and then I put a little hat on top. Now, I've seen some people not really do the squiggle at the bottom of the I, but they'll almost always have that little triangular hat on top. And when people talk about these, they say I hat. So that's kind of a good way to remember it. So that's the first part of the vector. Now, keep in mind there's also a vertical direction, so we're going to go plus 612.8. And now the vertical direction has a fancy letter with it, just like the horizontal direction. But for vertical, it's going to be J. And this is how I like to do my J's. So some don't have the squiggle kind of at the start there, but again, they'll always have the hat. And then since our vector is only in 2D, there's no vertical, vertical, I don't know how to describe the out of plane direction in the third dimension. So our vector stops here, so we could put the squiggle brackets. And now there's one thing missing, and you guys may already pick up on it. It's the units. So notice how I put 514.2 I. I didn't put 514 pounds times I. What you do for units for these vectors is you just put them at the end. So we have our 514.2 I plus our 612.8 J, and then at the end of the squiggle bracket, we put the unit, so pounds. So this tells us right here that our vector goes 514.2 pounds horizontally and then 612 pounds vertically. And in the end, that'll actually be the same vector as the 800 pounds at a 50-degree angle. But how we get that from this, I'll show you a bit later when we find the resultant. But I'm just going to touch up on a couple things here. And this is a little bit of a trick of the Cartesian vector notation, which you guys are going to want to learn. So first trick, I guess this part isn't the trick, but the next part is. The first thing is if we did have a vertical direction, and you guys may think, ooh, vertical, don't want that. Well, spoiler alert, it's coming very soon, I think the next week's lecture. So don't get too comfortable with 2D. We go to 3D. But I'll let you guys in on a little secret, which you guys will probably be happy about, is after the midterm, we go back to 2D and we stay there. And, well, the reason why is, well, at least the reason I view it is in our actual engineering. So take it from me, I'm a structural engineer. What we want to do, even in real world design, so actual buildings, is we want to take all our complex cases, all our three-dimensional cases, and we actually solve a lot of them using 2D models. So learning 2D is actually very valuable. I know a lot of you newer students will think, oh, 2D doesn't really matter because it's not realistic. Well, it's actually really funny because it's actually extremely realistic. And even in full-fledged building design, we go back to two-dimensional models because it's just simpler, it's easier to understand. So knowing 2D is a good thing. But like I said, sorry, I'm getting ahead of myself. If we were in 3D right now, our little fancy letter will be a K. So if this was 3D, what we do is we have a little K and a hat. So that's for 3D right there. If you guys want to remember that, perfect. If you guys don't, that's completely fine because you guys will see it lots when we get to the three-dimensional stuff. The second part, and this is the important part, so if you're going to take something away, take this away. You notice how this is a positive value, and then I put a positive value for the J. That's because our vector is going up and to the right. And in engineering, I'll just draw an axis to show you. So, as some of you may know, each axis has a positive and negative value. So this up here is going to be Y, this is going to be X, this is going to be negative X, and then down here is going to be negative Y. So our vector right here, the blue one, was really nice because it went both positive X and positive Y. Now, let's say that we had the same vector, same angles and everything, so its components are going to be the same, but it went this way, like this. Well, what you do is the components will still be the same. You can go 800 times cosine of 50, 800 times sine of 50. The components will be the same. But what you do is, this is more based on now your intuition. You know that it's going into the negative x direction. So in our F1 here, you'll actually put negative 514. And in our J, since it's also going in the negative y, you'll put minus 612. So you got to keep that in mind because if you don't get those right, then it'll actually mess up your final answer. So this is the part of the intuition where you just have to know which way it's going. Now I'll give you guys a little bit of, well, I don't know how to put this, but for 2D it's simple. It's always simple. You can tell which way the vector is going. I know that you guys go, oh, it's going to the left, it's going to be negative, or it's going up, it's going to be positive. But in 3 dimensions, it may be a little bit more difficult, especially when the vectors get a little more complex. A lot of the formulations in 3D will actually help you figure it out. So if you're worried about 3D, which don't be worried about 3D, everything's going to be fine. But if you are worried about 3D right now, just relax. It'll all be fine, and we'll get to it when we get to it, but don't worry. Just focus right now on the 2D. And so far, if you can get to where I've gotten right here, then all your problems are solved. Like this, you got it. This will be easy. So let's move on to the second vector here. I won't use red because I'm using that with the letters. I'll go orange. Haven't done orange. So our second vector, which will now be the orange vector, comes across like this. So again, this has two components. It's going to have a vertical component. Oh, went to the eraser. So if I dash up, it's going to have a vertical component, which like so. And if this is F2, we'll just call this F2. Then we'll call this one F2Y. And then of course it's going to have a horizontal component as well. And we'll call this one F2X. And what's nice about this triangle is we're already given the angle, the 35 degrees, and it's with the x-axis. So everything works out really, really well. So if we go down to the math of it, we know that F2x is going to be equal to the magnitude, which is going to be 500 in this case. And what's nice is if the angle's with the x-axis, to find the x component, we always just use cosine. So cosine of the angle, which in this case is going to be 35 degrees. And that, once you type it into your calculator, is going to be 409. So 409.6 pounds. And similarly, we can do the same thing for the vertical component. So F2y is going to be equal to the magnitude, 500. And the only thing that changes here is this going to be sine times sine of 35, which is going to be equal to 286.8 pounds. So there's the component. So what we can do now is we can say that F2, and since we're putting it in vector notation, put the arrow on top, it's going to be equal to squiggly brackets. So this is where the intuition comes back. Let's look at our vertical component. It's going to the right. Therefore, it's going to be a positive value. So we'll just say 409.6. Oops, not back to the eraser. 0.6. And this is very important, which is why I'm putting it in red. It's in the horizontal direction. So we put our little I, and then go back to our intuition. This vector, the y component's actually going downwards, so it's negative. So we go minus the 286.8 pounds. Again, we don't put the pounds to the very end, but since it is a vertical direction, we should need to put the J on it. So J. And then we finish it up by ending the squiggle bracket and putting the unit. So pounds. And this right here, you guys are pretty much done at this point because the last part is simple addition. So this is why I always told you guys in the previous videos, and I'm hinting at it now, is I love this method the best because to find the resultant of the two, the only thing we have to do, and yes, it is this easy, is just add the components of each. So let's put the component as, let's go pink. So we know that the resultant force is going to have a horizontal component, which we'll call FRX. So the resultant force has an x component. And if it's, and that's going to be equal to, and this is very simple, it's just going to be F1x plus F2x. If you were adding 3 vectors, it'd be plus F3x, 4 vectors, F4x. So it's really simple. You just take all the components of the vectors you want to add and just literally add them together. So in this case, our F1x is going to be the 512.4. So 512.4 plus our F2x is going to be the 409.6. And since we're only adding those 2 vectors, that's all we need to do. So we add them up together, we're going to get 923.6 923.8 pounds. So that was really simple, and that's our our horizontal components for our resultant vector. So this is why it's also nice labeling it with the eyes, is because it shows you, it reminds you which ones are the horizontal ones. If you don't put the eyes or the J's, you may get a little confused. You may actually put a vertical component in there. It's going to mess the whole thing up. So I'm just going to switch to a different color. Don't know what this is, but let's try it. So similarly, FR, so the resultant force, well, basically just looks kind of bluish black. Yeah. FR, and then the vertical component is going to be equal to F1y plus F2y. And again, if there was more vectors, then we just add the extra components. So F1y, we scroll up, is going to be 612.8, so 612.8, and then we plus, because it's vector addition, we just go plus, and then we look here. Now this component is 286.8, but it's negative. So what you do here is I just put in brackets minus 286.8. Now you guys are very smart too, so if you guys really wanted, you don't have to go plus and then a negative number, you can just go minus the number, but completely up to you guys. For vector addition, I always like just to go plus, plus, plus because it's addition, and then I just factor in if it's negative or positive into the actual answer. So what happens here is when I add those two together, I get 326.0 pounds. And now this right here is the y component of our resultant vector. So now this is really, really, really nice, because if we were to create the axis again, so let's just go down here and create our x and y axis, because this right here isn't the final answer. These are the components. It's not the final magnitude. And now you guys may be wondering, well, we took our vector f1 and split it into components, but now how do we take the components and put it back into a single vector? Well, it's actually really easy, and I'll show you guys kind of the proof for this first, but there's just formulas for it that you guys don't have to do this proof, but here's the proof. So FRX is 923.8 pounds, so we know that it goes in the positive direction, 928, so it's quite a long one. So this is FRX, and we know it's the horizontal component, and this is 928.8. Oh, sorry, 923.8 pounds. Excuse me. 923.8. And then we know that the vector also goes, oops, that's the wrong color. It goes up by 326. So this will go up by 326. So this is 326.0. And what we do now to find the resultant vector is we just, let's do it in purple. Is we start from the axis and we just go right to the end. Perfect. So this right here, this purple vector now, this is our FR, our resultant vector. So if we know the length of two sides of a right triangle, then we can solve for the third length. And since this right here is the hypotenuse, we know that FR squared is going to be equal to, and then this is the actual formula for 2D, it's just going to be equal to FRX, so the x component squared, plus FRY squared. So it's just c squared is equal to a squared plus b squared. It's that simple. So if we were to do this here, we know that FR, and I'm just going to move the squared sign to the other side just to kind of skip a step. So this is the magnitude of FR. It's going to be equal to those two sides squared. So we got the 923.8 squared plus, and then we got the 326.0 squared. And I'm just going to close the square root sign. Awesome. So we type that in our calculator. We're going to get that FR right here is 980 pounds. So if you guys will go back to the last example, you'll find that using the parallelogram method, that these answers are actually identical, and they should be. Both methods are completely valid. They'll give you the same answer. I like this one more personally because even though I'm dragging this on to be a half hour to 45-minute video, this question actually will take you guys 5 minutes. You find the two components of each vector, you add them together, and you throw them into this formula to find the resultants. It's because I take forever to explain things. Now, this is the magnitude. So this is great. We wanted the magnitude. However, the problem also asks for the angle. So I'll do the angle as, I don't know, brown. I feel like I gotta redo this color palette because this just looks like some weird neon sign. But all right, continuing on. It's the same thing with trig. If we know two sides of the triangle, so let's say this side and this side, we can solve for the angle. Now, actually with you guys, if you already know that the hypotenuse is 980, you can do it three ways. You can do it sine, cosine, or tangent. Now, this is my recommendation. You guys don't have to do it because all three are valid. I would go with the tangent method. Because let's say you're finding FR and you get your answer, but you made a slight error in your calculator and your FR is not correct. Well, then your final angle will also be incorrect because you're relying upon that answer if you use sine or cosine. So that's why I like to use tangent, because we know that the tangent of theta, so a theta, is going to be equal to the opposite over the adjacent. So this is going to be FRY over FRX. And what's nice about this formula is it's always true for 2D again. Always true, which is perfect. So we know that to find theta, it's just going to be the inverse tan, -1, and then we put in our two values, so we're going to have 326.0 all over 923.8. So we throw that in our calculator, we'll get the angle to be 19.4 degrees. So therefore theta equal to 19.4 degrees. I guess I'll underline it just to help show it. And if you guys remember, this is the exact same angle again as the parallelogram method. So it shows that this method's completely accurate. Again, I prefer it. I find it simpler, but it's really up to you guys. It's whatever you guys think is the best, I guess. So our final thing that we have to do, we have to state our final answer, so that we're going to just say FR is going to be equal to 980 pounds. And we know that it's 19.4 degrees measured counterclockwise from the positive x-axis. And then if you guys want to be nice, which please be nice, I'm begging you all, please be nice. Final thing to do, just box your answer. It helps us a lot. And that's it. So, again, the method I find is much simpler than the parallelogram method. The steps are always the same. They're always simple. What we want to do is find the components of our vectors, add them together, and then what we can do is just use these two formulas. So we'll go formula 1, because they don't change. I showed the proof for them, but you guys won't have to go and prove them. And you got formula 2 to solve for the magnitude and the direction. And that's it. So nice and easy. All right, so this concludes the video. In the next video, what we're going to do is resolve the example with 3 vectors using the parallelogram method, but this time with the Cartesian vector notation, or CVN method, just to show you guys, even though I know some of you may think that the parallelogram method is just as easy for 2 vectors, which probably for 2 vectors it is. 2 vectors is a very simplistic case. When we get to cases where there's 3 vectors, the CVN method is actually much better and much more time efficient. And especially because in real life, you're not going to get 1 vector, you're not going to get 2 vectors or 3, you're dealing with hundreds or even thousands of vectors. All right, so thanks again, guys, and I will see you guys in the next tutorial.